You know, every digital picture you've ever seen, it has a secret. Hidden inside all those pixels is a second, invisible image, a kind of hidden twin that holds the key to its basic structure. And once you figure out how to read that hidden language, you can do things that honestly look like straight-up magic. Let's start with a problem that seems impossible to solve. Take a look at this. I mean, this image seems completely ruined, doesn't it? It's covered in this ugly repeating pattern. Is there any way at all to recover the original photo that's buried under there? At first glance, you'd probably say, no way. But what if I told you we could fix it perfectly?
And just like that, there it is. The pattern is just gone. Now, this isn't some clever Photoshop trick or some AI just guessing what should be there. Nope. This is the result of a really powerful scientific technique that lets us see and even speak the hidden language of images.
So how on earth do we do it? Well, the secret is all about unlocking something called the frequency domain. It's time we all met our picture's hidden twin.
Okay, so the tool that makes all this happen is called the 2D Fourier Transform, or DFT for short. Now, don't let the name scare you, and please don't worry about the math. Just think of it like a universal translator. It takes a regular picture, the one made of pixels, and it translates it into a totally different kind of image, a frequency map. And this map shows us what the picture is actually made of.
So, what are these maps actually showing us? Let's take something super simple, like a smooth gradient. Look at its frequency map. It's just one bright dot right there in the middle. This tells us something really important, that slow, gradual changes in a picture are what we call low frequencies, and they always hang out right in the center of the map.
Okay, so what about the opposite? What about a super complex cityscape, packed with sharp edges and tiny details? Whoa, its frequency map is this wild explosion of points and lines, spreading way out from the center. And that shows us that all those sharp details, the edges, textures, all that good stuff, those are the high frequencies, and they live in the outer parts of the map.
All right, so once you get that idea, that pictures are basically a mix of low and high frequencies, you can start thinking about them in a completely new way. And it's a way that, well, it might feel surprisingly familiar.
Here it is. This is the key to everything. The absolute best way to get this is to think of that frequency map as a graphic equalizer for your image. Yeah? Just like the one in your stereo. But instead of messing with audio, we're tweaking the picture itself. Let's really break that down. In music, right, low frequencies are the bass, that deep, thumping foundation of a song. In a picture, the low frequencies are the same idea. They're the big, smooth areas. Think about the sky or a soft shadow, a gentle change in color. Then you have the high frequencies. In audio, that's the treble, the sharp, crisp sounds, like a cymbal crash. And in a picture, it's the exact same concept. It's all the sharp details, the edge of a building, the texture on a brick wall, the letters on a sign. So, with this mental equalizer in our hands, we can basically become digital sound engineers, but for our photos. We can start tuning them with filters to do things you probably do all the time, like blurring and sharpening. And the process is pretty much always the same, which is cool. First, you start with your picture. Then, you generate its frequency map, its hidden twin. Step 3, you apply a mask, which is just a fancy way of saying you block or boost certain frequencies. Then you reverse the whole thing, using an inverse transform to turn it back into a regular picture. And boom, you get your final edited image.
So let's say we want to blur an image. Okay, using our audio analogy, that's like turning the treble way down on a song, making it sound all muffled and bassy. To do this with an image, we use what's called a low-pass filter. It lets the low frequencies, the bass, pass right through, but it totally blocks the high frequencies.
And what's the result? Well, when you strip out all those high-frequency details, all you're left with are the smooth, low-frequency parts. The image gets blurry. And that, right there, is fundamentally how pretty much every blur tool works. Okay, so now let's flip it. A high-pass filter is like cranking the treble all the way up and cutting out the bass completely. It blocks all that smooth, low-frequency stuff and only lets the sharp, high-frequency details get through.
And the result of this is pretty fascinating. When you only keep the high frequencies, you get an image that's basically just the outlines and fine details. Now, this might not look very useful by itself, but trust me, this is the absolute first, most critical step in almost every single image sharpening tool out there. Okay, so blurring and sharpening, that's one thing. But what about that impossible photo we saw at the very beginning? For that, we need to go beyond a simple equalizer and start doing something that feels more like, well, like digital surgery.
Let's go back to that ruined photo. It had a very specific, repeating noise, right? That grid pattern. Well, when we look at its frequency map, something incredible happens. That single, repeating pattern in the picture creates a few super specific, super bright dots on the frequency map. That pattern is those dots. They're one and the same.
And here it is. This is the magic moment. If that ugly noise is just those bright dots, what happens if we just erase them? We can apply what's called a notch filter. It's like a tiny surgical mask that just blacks out those specific frequency spots. We do that, reverse the process, and it's gone. By surgically cutting out the frequencies of the noise, we remove the noise from the picture itself, leaving everything else perfectly intact. How cool is that?
Okay, fixing pattern noise is incredible, for sure. But frequency analysis has an even more mind-bending trick up its sleeve. It can reverse things that seem truly irreversible. I'm talking about blur.
So let's ask a new question. We know now that blurring a picture is basically just a type of low-pass filtering. But what if we know exactly how it was blurred? Like, say, we know the exact motion of the camera. Could we then create a filter that does the perfect opposite? A kind of inverse filter to undo the damage completely?
And the answer, amazingly, is yes. This technique is called deconvolution. By figuring out the exact nature of the blur, we can apply a super precise inverse filter in that frequency domain, and we can actually reverse the effect. Look at this. Text that was totally unreadable because of motion blur can be brought back into perfect focus. It's just an astonishingly powerful idea.
Now, I should add a quick dose of reality here. This simple inverse filtering is incredibly cool, but it's also really sensitive to any random noise in the picture. It can actually make things worse by amplifying that noise like crazy. So in the real world, engineers use smarter tools, like something called a Wiener filter. It does a similar job, but it's way more robust and gives you a much cleaner result. So, why does any of this really matter outside of a science lab? Well, because this stuff is being used everywhere, all around you. It's used to sharpen images from the Hubble Space Telescope, to pull more detail out of medical scans like MRIs and X-rays. It's used to clean up blurry footage from security cameras, restore old and damaged photographs, and yeah, it's even inside the sharpen tool on your phone's camera. It's one of the true unsung heroes of our digital world.
And all of that brings us to one last thought. We started this journey with something that looked like pure magic, but we found out it was just a different language, the language of frequency. But when you realize how easily we can edit, enhance, and even bring images back from the dead by rewriting their most fundamental code, it leaves you with a pretty deep question. In a world where we can perform this kind of digital surgery, what does it really mean for a photograph to be true anymore?